PhysicsBootcamp Test 3 review. This problem is a good example of a problem that utilizes the Bernoulli equation for flowing fluids. Okay, you have a pipe. The pipe has a certain opening here, and then it narrows as it goes here. You have water coming in here, or it could be some other kind of fluid, and then the water goes down, and we want to know what is the velocities here, right? So the problem says the pressure at point 1 is 2 atmospheres. We can write one like this here. Point 1 is 2 atmospheres, and the pressure at point 2 is 1.5 atmospheres. So here there's more pressure pushing than here, okay? So this one is 2 atmospheres, this is 1.5. The area of the opening 1, this area is 10 square meters, which is pretty big. And the area of opening 2 is 2 square meters. Okay, this one is narrower. Opening 1 is 10 meters higher than opening 2. So this one, 10 meters higher. So basically we're doing from the center of this to the center of that. Okay, that is 10 meters. From center to the center. Find the velocity v1 of the incoming water. So what equation do we use? Well, we use Bernoulli's equation, which is pressure at point 1 plus the density of water plus g plus height of point 1 plus half of rho v1 squared, density of water. The Bernoulli's equation is pretty much a restatement of the conservation of energy. This is the potential energy of the water, kinetic energy of the water, and then all the external forces on the water, which is we call pressure for water. That must be equal to P2 plus density of water, GH2. So it must be equal to the forces on the water at point 2 plus the potential energy of the water at point 2 plus half rho V2 squared. The other equation we got to use is that we believe the water is a good example of an incompressible fluid. So the volume flow rate, Q, which is A1V1, must equal A2V2. What does volume flow rate mean? Well, it's the surface area, the cross-section, times the velocity of the fluid. Its units is meter square times meter per second. Well, what does that mean? It's meter cubed per second, right? So what is volume flow rate measuring, the Q? It's measuring how much volume of fluid is flowing per unit amount of time through a certain cross-section, right? How much volume of fluid. So if the fluid is incompressible, it can't be compressed. So what's going to happen? Well, the volume flow rate is going to remain constant, right? So what does that mean? If the area goes down, the velocity is going to tend to go up, right? So when a fluid is made to constrict, it's going to tend to go faster, right? This is kind of basically like what you do when you're watering your lawn. Maybe you're watering your lawn with a hose, and you want the water to go farther out. So you kind of put your finger in the opening, you narrow the opening, right? You put your finger and then it shoots out much more, farther, right? So the volume is made to go through a smaller opening and it goes much faster. That's because the volume flow rate is constant, right? Okay, so in this case, what's going to happen? We have A1 is equal to 10, right? V1 is equal to, we don't know. A2 we know is 2. V2 we don't know. So we divide this and we get 5. So V2 is equal to 5V1. So the only thing we know now is that this velocity must be 5 times this velocity, right? In order for it to be incompressible fluid. Then we take that and we put it into here, into the Bernoulli's equation. Okay? So what's the pressure at P1? 2 atmosphere, right? But can we put 2 here? No, because this is metric. This is metric. Everything is metric. You can't put 2 and 1.5 here. So remember that 1 atmosphere is 1.013 times 10 to the 5th pascals, right? So 2 atmospheres is 2 times that. Density of water, 1,000. G is 9.8. What's H1? That's 10 meters, right? Plus half, 1,000. V1 squared. What's P2? Well, P2 is 1.5 atmospheres. So it's 1.5 times this value. What's the density water H2? Well, H2 is 0 because it's the lower one, right? So it's going to be just 0 here. And then you have half of 1,000. Now what's V2? Well, V2 is 5V1. So we square that, right? 5V1 squared. So you have to square the 5 as well, right? So let's erase some stuff here. Okay, so 2, now notice this is a half, so basically what we could do is we could take this 1.5 and put it on this side, so we have 2 minus 1.5 of 1 atmosphere. 1,000, 9.8, 10, what does that give you? Well, that gives you, the 10 makes this 98, 98 times 1,000, 98,000. Then you have, now we got rid of this, we got rid of this. This one we can take to the other side. So we're going to have 1/2 1,000. 5V squared, that's going to be what? 25, right? 25V1 squared minus, and then when you take this one to the side, you have 1/2,000 V1 squared. So then what is this? Well, we can actually calculate this. This is a half, and then I can add 98,000 to this. So 0.5 times 1.013 times 10 to the power 5. So this one here gives me 50,000, 50,650. You add to that 98,000, you get 148,650 must be equal to half of 1,000 is 500. Half of 1,000, 500. So we have to do 500 times 25, right? 500 times 25. That gives you 12,500. And then you subtract 500 from that. You get 12,000. And then that's equal to V1 squared. Okay, well, you could divide this into that and then square root it, right? 148,650 divided by 12,000 square rooted. So V1 must be equal to 3.52 meters per second. V2 must be equal to what? 5 times that. 17.60 meters per second. So this one's going to be going 3.5. This one's going to be going 17.6, much faster. Okay. So it's going to be going. Yeah, that's the answer. This one's going to be going much faster for 2 reasons, right? First, it's losing potential energy, so it's going to be gaining kinetic energy, right? Out of that, we expect it to go faster. And not only it's going to go faster because of that, but because it's narrowing. When it narrows, it tends to go faster, right? What would happen if this was going up? Okay? Then it would slow down due to the fact that it's going up, but it would speed up due to the fact that it's narrowing, right? How would we change the equation? This part here, rho WGH, now we would put negative 10 here, right? It starts out 10 meters below. So this would be negative 98,000. How would that change the answer? Well, you would have 0.5 times 1.013 times 10 to the power 5 minus 98,000. So actually this would come out to be negative 47,350. So what would that mean? Well, that means the water never gets there, right? The water just never makes it there. So what would you have to do in order to make it go up? Let's see here. What would we have to do? Here is what we would have to do. We would have to make the pressure here P2 and then P1. Remember, P1 was 2 atmospheres. P2 was 1.5 atmospheres. We would have to make this one less pressure. You see, this pressure is the one pushing this way on the fluid. This pressure is the pressure pushing it this way. So if we want to make it go up, we would have to make the pressure pushing this way less. So let's say we make this 1.0. Okay? And then we make this still 2. Then is it possible it's going to go up? Well, how would that affect it? Well, it'd be 1.0 here, right? Then when we subtract 1.0, we just simply get 1. So the difference of the two pressures is 1 atmosphere, right? So we would end up 101,000. This time we're going to get positive. It's going to be 101,300, right? This number minus 98,000. It's going to be a small number. 3,300. Okay? Okay, so it's going to be 3,300. Over here, nothing's going to change because we still have 25. The ratio of the areas is the same. So we're going to get here V1 is equal to what? Well, 3,300 divided by 12,000 square rooted. V1 is equal to 0.524 meters per second. V2 is equal to what? It's going to be 5 times that. 2.62 meters per second. Okay? So if the water starts out here kind of slow, but this is pushing it 2 atmospheres, then here the pressure can be 1 atmosphere pushing back out, and then the velocity will be 2.62. So actually what this could be is that it could actually be coming from underground, and then this could actually be the ground right here, the ground level, right? So if you had a source of pushing the water out, then it would go, it would go, it would go, it would come out of here, and then the pressure here would be what? It'll be atmospheric pressure, so because it's exposed to the air, right? So you could have an underground source pumping the water out, okay? It would be twice the pressure of atmospheric pressure, and then here will be the same as atmospheric pressure. If the velocity there starts out at 0.524, the velocity coming out will be 2.62, okay? So you could kind of have fun with these kinds of problems, do pipes, the pipes that go down, pipes that go up, pipes that get bigger, pipes that get smaller, and then apply Bernoulli's equation and the equation of continuity for the volume flow rate. Okay, so thank you very much.